Welcome to the Explainer. Today we're going to translate what is essentially the hidden universal language of space engineers. We're talking about the decibel. We are going to uncover how this incredibly simple mathematical trick takes the vast, completely incomprehensible scales of the universe and makes them manageable enough to fit right inside the smartphone in your pocket.
Okay, let's just dive right into this totally mind-boggling number, 10 to the negative 16th watts. Think about that for a second. That is a decimal point followed by 15 zeros and then a 1. This is the microscopic, unimaginably tiny amount of power that a GPS signal from space actually has when it finally hits Earth. It's a perfect example that proves just how awkward normal math becomes when you're dealing with a cosmic scale. So that brings us to section 1, the space math problem.
To truly appreciate why engineers needed a completely new way to talk about numbers, we first have to understand the massive problem they were facing with satellite transmitters and these ridiculously weak space signals. When you're trying to calculate systems that span from high-wattage space transmitters orbiting the planet all the way down to that microscopic speck of a watt we just talked about, standard linear math is, well, frankly, it's terrible. The ranges become completely unmanageable. Trying to multiply a number with 15 zeros by a regular whole number is frustrating, it's error-prone, and it's an absolute nightmare for calculators.
Which leads us to section 2, enter the decibel.
So, what's the big secret? What rescues these engineers from just drowning in a sea of zeros? It's the dB, or the decibel. By definition, it's a logarithmic unit used to express a ratio between two quantities, things like power, signal strength, or gain and loss. Notice that keyword there, ratio. The decibel isn't an absolute physical unit like a pound or an inch. It's purely a ratio. It's this genius way to compress absurdly huge or tiny scales into something a human brain can actually wrap its head around.
And this comparison right here brilliantly illustrates the difference. Saying signal A is 1,000 times stronger than signal B is super clunky, especially if you have to multiply that by another 1,000 down the line. But saying signal A is 30 dB higher gives us a clean, easy-to-read metric. Instead of clunky multiplication of massive numbers, using decibels gives us a streamlined, highly practical way to compare signals.
All right, moving to section 3, the engineer's cheat codes.
Now that we know what a decibel fundamentally is, let's look at how engineers actually use it out in the real world as the ultimate math cheat code. Yes, okay, there is some math underneath it all, like this logarithmic power formula. It works by comparing a measured power to a reference power, calculating the base 10 logarithm, and then multiplying by 10. But here's the secret. Engineers quickly bypass doing this complex formula every single time, and they rely on practical shortcuts instead.
Just a quick side note on this, if you're measuring voltage or current instead of power, the formula shifts just a little bit. You multiply by 20 instead of 10. Why? Well, because power is proportional to voltage squared, and the mathematical properties of logarithms pull that squared exponent out to double the multiplier. But again, honestly, you rarely need to crunch these raw logs by hand.
Because here is where we find the rules of thumb that let you ditch the complex logarithms entirely. Just memorize these 4 simple facts. Plus 3 dB, that means you double the power. Minus 3 dB, you cut it in half. Plus 10 dB is 10 times the power, and minus 10 dB is 1/10 the power. With just these 4 things in your pocket, you can quickly estimate almost any power change entirely in your head. You can see how these rules of thumb stack up in a perfectly mapped out sequence. Look at how a ratio of 10 times is plus 10 dB, 100 times is plus 20 dB, and 1,000 times is plus 30 dB. It proves that as your power ratio skyrockets into the millions or billions, your decibel number grows in a very manageable, orderly way. You literally just step up the ladder, 10, 20, 30. And this builds into the ultimate life hack. To find output power the old way, you'd have to multiply the input power by multiple gain percentages and divide by losses. It's a huge mess of decimals. But with decibels, we literally transform terrifying strings of multiplication and division into simple first-grade addition and subtraction. Output power is just the input plus the gains minus the losses. It's beautiful. Now, since decibels are inherently just ratios, meaning a comparison between two things, engineers will attach specific letters to the end of dB to give that ratio a solid anchor in reality. So dBW means the power is specifically referenced to 1 watt. dBm means it's referenced to 1 milliwatt. We also use things like dBi for antenna gain, or SNR to measure a signal against background noise. Those letters basically just tell you exactly what physical reality you're starting from. All right, let's jump to Section 4, the GNSS signal miracle. To see this whole language in action, we have to look at one of the most awe-inspiring achievements in human engineering, global navigation satellite systems. A typical GPS signal received on Earth is around -130 dBm. Let's break that down. The M means we start at 1 single milliwatt. If -10 dBm is a tenth of a milliwatt and -20 is a hundredth, dropping all the way down to -130 translates to a signal drastically weaker than a single milliwatt. Like we said earlier, it is basically a phantom signal.
And yet, the true miracle here is that despite the signal being a faint whisper, hidden inside the Earth's background static, your phone's receiver uses this precise math, correlation, and signal processing to effortlessly extract that data and pinpoint your exact location. It honestly feels like magic, but it's just brilliant math.
Now for Section 5, link budgets made easy. Let's actually apply our new Decibel cheat codes to a real-world space communication problem. It's called a link budget. A link budget is simply the math an engineer does to ensure a signal can successfully travel from point A to point B without fading away entirely. Imagine a scenario where we have a transmitter pumping out 20 dBm of power. But the signal loses a little bit of energy traveling through the wiring, so we have a cable loss of 2 dB. Luckily, though, the antenna focuses the beam, giving us an antenna gain of 5 dBi. If we were using standard percentages to figure this out, this would be a massive headache. But thanks to the magic of the decibel, calculating our final output power isn't a complex physics equation. It's literally just 20 minus 2 plus 5, leaving us with 23 dBm. We just did space communication math using the exact same arithmetic you would use to count apples. Because of this productive laziness, this deep desire to make impossible math entirely practical, the decibel is absolutely everywhere. It acts as the fundamental language connecting RF systems, radar, satellite communications, GNSS tracking, telemetry links, and all antenna and noise analysis. For space systems, the decibel isn't just a unit of measurement. It's the universal language of the discipline. Which really leads us to a pretty mind-blowing thought. If engineers can extract perfect navigation data from a -130 dBm whisper from space, what other invisible signals are you walking through right now? The next time you use GPS or connect to Wi-Fi, remember the secret decibel math making it all possible. It really makes you wonder about the invisible, perfectly calculated web of signals surrounding us every single day. Thanks for joining me on this explainer, and keep questioning the unseen world around you.